Swayam Prabha. Digital India. Educated India.
Welcome to lecture 26 of the course on multivariate data mining methods and applications. The title of this lecture is Recurrent Neural Network and Projection Persuit Regression. Often we have sequential data and there is some kind of interdependence among the observations. Means the current observation is somewhat related to the past observations also. Now, the recurrent neural network provides a good option for modeling such kind of sequential data. The recurrent neural network has internal memory of past observations, and this is the specific characteristic which makes it capable of modeling such kind of sequential data with internal dependence. So, in this lecture we are going to discuss the architecture of recurrent neural network. We will also discuss the projection persuit regression. Actually, if the relationship between output variable and a set of input variables is complex, then apart from the artificial neural network, one can also use the projection persuit regression. So, projection persuit regression is actually a statistical technique to model such kind of complex relationships between the output and input variables. Now, before going to the recurrent neural network, first we consider the convolution neural network and the advantages of weight sharing in convolution neural network. Now, suppose you have a 4 cross 4 image, then if you are using a 2 cross 2 filter and it has no stride, then the filter with 4 weights, 1 per pixel is applied 9 times and it requires 36 weights in all. So, remember that here each filter may have different weight and we have 4 weights per pixel. So, in all you have to use 36 weights. Now, if same weights are used for all the 9 filters, then it requires just 4 weights. So, this is the advantage of weight sharing. It reduces the number of weights to be learned, and by reducing the number of weights to be learned, it reduces model training time and cost also. So, this is the advantage of weight sharing. Further, it makes feature search insensitive to feature location in the image. So, this is another advantage of weight sharing. Now, fully connected layer. In a fully connected layer, the computation of any element in the output x l plus 1 or y is the output, requires all elements in the input x l. So, y or x l plus 1 is connected with all elements in x l. and usually we require a fully connected layer at the end of a CNN model. So, for example, if the output layer contains distributed representations of the input image, then use all these features in the current layer required to build features with stronger capabilities in the next one. And then for this purpose, you can make use of a fully connected layer. So, a fully connected layer is useful for this purpose. Now, by local connectivity we mean each neural is connected only to a subset of the input image. And then by parameter sharing, we mean sharing of weights by all neurons in a particular feature map. So, we are sharing the weights, and then if we are using sharing of weights, then it helps to reduce the number of parameters in the whole system, and it also makes the computation more efficient. So, just like in a convolution layer, what we do? We share the weights, we apply the same weights to different windows for obtaining the output. We use the same kernel for each window. So, we actually use parameter sharing or weights sharing. Now, based on the assumption that if one feature is useful to compute at some spatial position, then it should also be useful to compute at a different position. So, basically this is the idea behind weight sharing. If one feature is useful to compute at some spatial position, then you can use the same weights to compute at a different position. Receptive field, say in a convolution layer, each neuron receives input from a restricted area of the previous layer, and this is actually called the neuron's receptive field. So, your receptive field is actually a particular window. For a particular neuron, your receptive field is inputs from a restricted area of the previous layer. In a fully connected layer, the receptive field is the entire previous layer. So, the output is connected with all the neurons of the previous layer. Pooling layer. Pooling layer is actually used to reduce the dimensions by combining the outputs of the neuron clusters at one layer into a single neuron in the next layer. You take outputs of neuron clusters at one layer, and then you combine it to a single neuron in the next layer. So, this is how we are reducing the dimensions. Local pooling combines small clusters, whereas global pooling acts on all the neurons of the feature map. We combine small clusters, then it is called local pooling, and if we are combining all the neurons of the feature map, then it is called global pooling. Now, the matrix with PL cross QL elements are divided into PL plus 1 cross QL plus 1 non-overlapping subregions of P cross Q in size. So, you have a matrix of this size. So, what we do? We divide it into P L plus 1 cross Q L plus 1 non-overlapping subregions, and each of these subregions is of size P cross Q. Then pooling operator maps a subregion into a single number. Two widely used pooling operators are maximum pooling and average pooling. We have discussed both maximum pooling and average pooling in the last lecture. Now, here is an example of image convolution. We have an image of cycas flower. This is the original image, and first we convert the image into a tensor format with 3 layers of color images RGB and 1 layer for grayscale images. Then each element represents a value between 0 to 255, and then first we use the convolution operator for detecting the edges. So, it approximates the gradient of the image intensity, and we use Sobel kernel matrix, which is a 2 3 by 3 kernels, one for horizontal changes and another for vertical changes. So, we have two matrices A and B. The matrix A has elements 1 to 1, then 0 0 0. So, second column is just consist of zeros, and the third column is -1, -2, -1, and B is actually transpose of A, and we use these two kernels. Kernel A actually highlights the horizontal edges, that is changes in intensity along the x axis, and kernel B highlights vertical edges, that is changes in the intensity along the y axis. And then Sobel kernel matrix is actually, it emphasizes the regions of high spatial intensity change in both horizontal and vertical directions. So, we are combining 8 by 8 pixel input matrix with a 3 by 3 kernel, and then your output is actually 6 by 6 matrix data, and then again we convert it into the form of image. Now, if we are using A, then we get this image, and this image actually highlights the horizontal edges. And if we use the kernel matrix B, then it highlights the vertical edges. We are using our program for the convolution operation, or if we change the kernel matrix, now we are taking this kernel matrix with elements 0 1 0 1 -4 1 0 1 0, which is again a 3 by 3 matrix. Then we get this image, and if we use this kernel matrix, then we get this image. So, in all these cases, the edges are highlighted in this image as well as in this image. Now, we use embossed kernel matrix. So, this matrix is employed for generating a 3D effect on an image. Here, the central element actually corresponds to the current pixel being processed, and surrounding elements represent the differences in intensity values between the current pixel and its neighboring pixels. Negative coefficient indicate regions of lower intensity and positive coefficients indicate regions of higher intensity. So, we use this kernel matrix and then we employ image convolution, and this is the image after convolution. So, it has 3D effect. Or sharpening kernel matrix. Sharpening kernel matrix actually emphasizes regions of high spatial intensity change in horizontal and vertical directions. So, it enhances the edges by increasing the difference in intensity between adjacent pixels. Here again the central element, which is 6, represents the weight of the current pixel, and surrounding elements, which are -1, -1, compute the difference in intensity between the central pixel and its neighbors. So, we have used this kernel and ultimately we get this image, which actually emphasize the regions of high spatial intensity in both horizontal as well as in vertical directions. Now, we come to recurrent neural network. Actually, both recurrent neural network and convolution neural network exhibit temporal dynamic behavior. So, both of these models can be used when the sequential data exhibits some kind of temporal dependence. Convolution neural network is a class of networks with a finite impulse response, and by impulse response we mean output of a dynamic system when presented with a brief input signal. You have a brief input signal, then the output of the system. Recurrent neural network is actually a class of networks with an infinite impulse response, and it is a bidirectional artificial neural network. Just like several time series models like autoregressive model or moving average model, where the current observation depends upon the past observation also. So, it is a bidirectional artificial neural network. It allows the output from some nodes to affect subsequent input to the same nodes. And then this property actually makes the model dynamic. Then it uses internal state, that is internal memory, to process arbitrary sequence of inputs. This is in particular applicable to tasks such as unsegmented connected handwriting recognition or speech recognition, or it is also widely used for modeling time series data when the relationships are complex in nature, relationships between subsequent observations are complex. Now, we consider different variants of recurrent neural networks. Say fully recurrent neural networks. In fully recurrent neural network, we connect the outputs of all neurons to the inputs of all neurons. Each neuron of the output is connected with input of each and every neuron. Then if we set some of the connection weights to 0, then we get the different special cases. So, all other topologies can be represented by setting some connection weights equal to 0. In particular, just in brief, I am going to consider two networks or two special cases of recurrent neural network. One is Elman networks and second one is Jordan's network. So, suppose x t is the input vector and y t is the output vector and h t is hidden layer vector. Further, f h and g y, these are the activation functions. F h is the activation function which we employ at the hidden layer and g y is the activation function which we employ at the output layer. Further parameter matrices and vectors are say capital B h, capital A h, small b h, capital B y, capital A y and small b y. Then the Elman neural network is defined as H t equal to F h capital B h x t plus capital A h h t minus 1 plus B h. So, for this hidden layer H t depends upon H t minus 1 also. So, it involves H t minus 1 and y t is equal to g y b y h t plus small b y. So, this network is the Elman recurrent network or Elman network. In Jordan network, H t is equal to f h b y x t plus a h y t minus 1 plus small b h. So, basically at time t, the output of the hidden layer which is H t, it also involves y t minus 1. The output vector at time t minus 1. Further, y t is equal to g y capital B y h t plus small b y. So, this is the architecture of Elman network. You have input node here and your input vector is x t. So, you have this input vector at time t, then it goes to hidden layer, you get hidden units here and then you have H t and in the output H t is also involved. Further, this denotes the delay units, this particular node. So, here you have hidden units, then delay unit means you have H t minus 1 and H t involves H t minus 1 also. So, the current hidden unit depends upon the past hidden unit H t minus 1 and ultimately you get the output y t. Whereas, in Jordan neural network you have input. So, you have input vector x t here, then it goes to hidden units, hidden layer and your hidden units are again H t. So, you have H t here and then you reach the output layer and for the delay units you have y t minus 1 and ultimately the hidden units depend upon y t minus 1, the delay value of y t. Now, we come to projection pursuit regression. Now, suppose x is r cross 1 input vector and y is the target variable and s is equal to 1. So, the target variable is continuous say, and basically your objective is to evaluate the relationship between target variable and the set of input variables or the input vector. Now, if the relationship is simple, means suppose it is a linear relationship, then you can use the linear regression model, the multiple linear regression model. But suppose the relationship is complex, it is non-linear, then of course, you cannot use the multiple linear regression model, and then you require some alternative procedure. One of the options which we have discussed earlier is multilinear perceptron. Projection pursuit regression is another technique which can be used to model such kind of data. It is a statistical technique using which we can evaluate the complex relationship between y and x's. So, suppose your model is y equal to mu x plus epsilon, and then we simply assume that expectation of epsilon is equal to 0 and variance of epsilon is sigma square. So, actually this epsilon denotes the error having mean 0 and variance sigma square. So, expected value of y is mu x, and this is the regression function, and basically your objective is to estimate mu x. Now, if the relationship is linear, say mu x is equal to beta naught plus x transpose beta, then your problem is simple. You just apply the method of least squares for estimating beta naught and beta. But here the regression function is not simple. Even the form of the regression function is also unknown. So, your objective is to estimate mu x. So, obviously, like the method of least squares which we use for the multiple linear regression model, you will not get very simple solution. Now, suppose r is equal to 2 and the function mu x is equal to x 1 x 2. Then of course, you can write x 1 x 2 as 1 upon 4 x 1 plus x 2 whole square minus 1 upon 4 x 1 minus x 2 whole square. So, you have mu x equal to x transpose beta 1 square minus x transpose beta 2 square for specific choices of beta 1 and beta 2. Here of course, x 1 plus x 2 square is equal to x 1 square plus x 2 square plus twice x 1 x 2, and x 1 minus x 2 square is equal to x 1 square plus x 2 square minus twice x 1 x 2. So, x 1 square plus x 2 square will cancel out and ultimately you obtain x 1 x 2 here. We write x transpose equal to x 1 x 2, beta 1 equal to half transpose and beta 2 equal to half minus half transpose. So, basically what we get x transpose beta 1 equal to x 1 x 2 half. which is equal to half x 1 plus half x 2. Further, x transpose beta 2 is equal to x 1 x 2 half minus half. So, this is half x 1 minus half x 2. So, if we take square of these two and then we add, so ultimately you obtain x 1 x 2. Now, you can write x 1 x 2 as the sum of squares of the projections. Say x transpose beta 1 whole square, x transpose beta 1 is the projection of x using this coefficient vector beta 1, which is half half, and x transpose beta 2. Actually, any regression surface can be approximated by a sum of nonlinear functions g j of projections x transpose beta j. Now, this is the assumption on which the method of projection Persuit regression is based. Now, suppose for all m equal to 1 to capital M, omega m is r cross 1 unit vectors. Unit vector means omega m transpose omega m is equal to 1. Then omega m is actually the direction vector and it is unknown. Then in the projection Persuit regression method, we approximate mu x by using the form, say f x equal to summation m equal to 1 to capital M g m w m transpose x. So, you have this projection with direction omega m, and then g m is a function of this projection, and then we take summation over m. So, basically projection Persuit regression model is an additive model in the derived features omega m transpose x. So, these are different derived features of x. You may consider omega m transpose x as a particular feature of x, and then we are using this kind of activation function, which is of course a nonlinear function in general, and then we take a linear combination of these nonlinear functions, summation m equal to 1 to m g m omega m transpose x. So, g m omega m transpose x for all m equal to 1 to capital M, these are estimated along with omega m, and these are called a rich function in R R. And actually this varies in the direction defined by omega m. Omega m is the direction of the projection, and you have to estimate omega m as well as you have to find this function also g m. Now, suppose V m is equal to omega m transpose x. So, this is the projection of x onto omega m. Then we estimate omega m so that the model fits well. Now, suppose capital M is sufficiently large, then for appropriate choice of G m, the projection Persuit regression model can approximate any continuous function in R R. Again, this is the result which is quite useful in projection pursuit regression. For sufficiently large M and for appropriate choices of GM, it is possible to approximate any continuous function in RR by using the projection pursuit regression. And then projection pursuit regression model is quite useful in prediction also. Of course, the interpretation of projection pursuit regression model is usually not so simple, it is quite difficult, because each input enters in a complex way. Each time you are using the function GM. Now, for training the model, suppose you have training data xi, yi for I equal to 1 to n, and then you have to estimate the model, and your model is y I equal to summation m equal to 1 to capital M g m omega m transpose x I plus epsilon I. So, this is the model corresponding to the ith training data. So, obviously, epsilon I, that is error corresponding to the ith training data, is y I minus summation over m g m omega m transpose x I. So, this is the error term, and then we take square of the error and then we add over all the observations, and basically you have to minimize this error sum square over g m and omega m, and m varies from 1 to capital M. Then for given omega, we form say V I equal to omega m transpose x I. So, if omega m is given, then you get V I. Then what we do? We apply any smoother, such as say smoothing spline, we apply some spline function, and then we estimate the function g. So, initially we start with some value of omega, and we write V I equal to omega m transpose x I, and then we approximate the function g by some smoother, say some smoothing spline function, and once g is given, we can minimize s over omega using Gauss-Newton search. Now, suppose omega naught is the current estimate of omega. Then using the Taylor series expansion, we can write g omega transpose x I equal to, or approximately equal to, g omega naught transpose x I plus g 1 omega naught transpose x I omega minus omega naught transpose x I, where this g 1 actually denotes the first derivative of function g. And then we can write summation I equal to 1 to n y I minus g omega transpose x I whole square approximately equal to, we write g omega transpose x I approximately equal to this term, and then ultimately we get g 1 omega naught transpose x I square omega naught transpose x I plus y I minus g omega naught transpose x I upon g 1 omega naught transpose x I minus omega transpose x I whole square. You can easily verify it. Just you have to substitute the value of g from here. And then we run least squares regression with target omega naught transpose x I plus y I minus g omega naught transpose x I upon g 1 omega naught transpose x I on x I with weights G1 omega naught transpose xi square. So, now this is the problem of weighted least squares, and then you get the updated omega nu. Here this is known, and this is also known. So, you can easily run the regression or weighted regression. So, you get this new value of omega, then we iterate the two steps unless you get the convergence. Now, this model is actually built in a forward stage wise manner, adding a pair omega m g m at each stage. Then m is estimated as part of the forward stage wise strategy. Say your problem is also to estimate m. So, you can use forward stage wise strategy for estimating m, or you can use cross validation to determine m. Further, this model building stops when including additional term does not provide much improvement in the fit. So, if we further increase the value of m, that is, we are including an additional term and it does not provide much improvement in the fit, then we stop model building process. Usually, we use smoothing methods such as local regression or smoothing splines for evaluating the function g. So, basically what this projection pursuit regression model does, it first projects the data matrix of input variables in the optimal direction, say omega m transpose xi. So, you find the optimal direction and then applies smoothing functions to these input variables. So, to evaluate g m, we are using the smoothing functions. Then it uses univariate regression functions, which allows for simple and efficient estimation and effectively deals with the curse of dimensionality. So, this is the advantage of projection pursuit regression. Then projection pursuit regression also effectively ignores variables with low explanatory power. So, such kind of variables have either the weight or direction omega m equal to 0 or very low value of omega m. Then transformations of variables in projection pursuit regression are data driven, whereas in a single layer neural network transformations are fixed. So, these transformations are data driven. Further, both the approaches, the projection pursuit regression as well as neural network, they take non-linear functions of linear combinations. These linear combinations are actually based on the derived features of inputs. Then both the models work well for regression as well as for classification purpose. And these models compete with best learning methods on many problems. So, both the models can be used in most of the problems successfully for classification purpose as well as for regression purpose. Then both the models are effective in problems with a high signal to noise ratio. but both the models are not effective if the goal is to describe the physical process that generated the data and the roles of individual inputs. Actually, the form of both the models is quite complex, and it is very difficult to find simple interpretation of different coefficients or the process which has generated the data. Or even if you want to make interpretation about the roles of individual input variables, it is very difficult to interpret their roles. In this lecture, we have discussed recurrent neural network, which are specifically designed to handle sequential data, which involve some kind of interdependence. These networks have feedback loops, and these feedback loops actually make it possible to handle the sequential data and to model their interdependence. So, basically we have discussed the architecture of recurrent neural network, and then we have also discussed various applications of recurrent neural network. Then we came to the projection pursuit regression. In fact, in many practical applications, the relationship between the output variable, say y, and the input variables is quite complex. Then artificial neural network or the multi-layer perceptron is specifically designed to handle such kind of data. Another option is, or another actually statistical technique is to use the projection pursuit regression. Then we have also discussed how to estimate the weights of the projection pursuit regression model and how to estimate the functions involved in the projection pursuit regression model. So, I am going to stop here. Thank you.
Hello and welcome to this piece of literary snippet. As a student of English literature, the kind of poetry that we are most likely to encounter is perhaps the sonnet. Now, a sonnet, as some of us might already know, is a poem which is composed by putting together 14 lines of verse, and this style of poetry was first popularized by a poet named Petrarch, who lived in Italy during the 14th century. Now, legend has it that Petrarch once saw a very beautiful lady by the name of Laura, and Petrarch was so enamored by the lady that he wanted to compose poems to celebrate his love for her. But there was a problem because marriage was impossible. Petrarch himself was an ordained priest, and that prohibited him from marrying, and the lady herself was a married woman. But nevertheless, Petrarch went ahead to immortalize the beloved and his love for that lady in poetry, and the form that he chose was the sonnet. Since then, sonnets have traditionally been written about ladies who are of unparalleled beauty and about poets who are hapless lovers and who know that their love for their beloved would have to remain unrequited forever. Now, in England, the sonnet form came around 16th century, and its first practitioners were people like Sir Henry Howard, the Earl of Surrey, and Sir Thomas Wyatt. However, it was William Shakespeare who was to prove the greatest of English sonneteers. And in fact, the charm of those sonnets that Shakespeare wrote 400 years from now still can be felt. And if I read out to you one of Shakespeare's sonnets, you'll appreciate this better. This sonnet is usually known by the title, "Shall I Compare Thee to a Summer's Day?", which is also the first line with which the poem begins. Shall I compare thee to a summer's day? Thou art more lovely and more temperate. Rough winds do shake the darling buds of May, and summer's lease hath all too short a date. Sometime too hot the eye of heaven shines, and often is his gold complexion dimmed, and every fair from fair sometime declines, by chance or nature's changing course untrimmed. But thy eternal summer shall not fade, nor lose possession of that fair thou owest. Nor shall death brag thou wanderest in his shade, when in eternal lines to time thou growest. So long as men can breathe or eyes can see, so long lives this, and this gives life to thee. Now, as you might have noticed, that very much like the Petrarchan sonnet, this poem too speaks of an idealized lover who is more beautiful than a lovely summer's day. But also notice how, in the last few lines, the poem subtly shifts from praising the beloved to praising the poet himself. It is the poet who is going to produce the lines of poetry which will preserve the beloved's glory forever. And people will continue reading them even after the beloved has died. As the last couplet of the poem suggests, so long as men can breathe or eyes can see, so long lives this. And here this, of course, refers to the verse that Shakespeare composes and which we are reading today, 400 years later. So long lives this, and this gives life to thee. Shakespeare is well known for these kind of subtle plays with the conventions, these kind of subtle reversals of what is expected conventionally. But nothing is more striking than the sonnets that he composed on a dark lady. In these poems, we do not meet the traditional fair, idealized beauty, but rather a woman whose appearance might even be described as ugly. Here is a sample. My mistress's eyes are nothing like the sun. Coral is far more red than her lips is red. If snow be white, why then her breasts are dun. If hairs be wires, black wires grow on her head. I have seen roses damasked red and white, but no such roses see I in her cheeks. And in some perfumes is there more delight than in the breath that from my mistress reeks. I love to hear her speak, yet well I know that music hath a far more pleasing sound. I grant I never saw a goddess go My mistress, when she walks, treads on the ground. And yet, by heaven, I think my love as rare as any she belied with false compare. As you can see, the beloved described in this poem is nowhere as beautiful as a beloved of the first poem. Yet, the point that Shakespeare is making here is that though the image of the beloved is not as beautiful as it was in the previous poem, it doesn't stop her from being an object of love. Love, Shakespeare insists, has very little to do with the outward appearance of a person. And in many ways, this de-idealized beloved is perhaps a person with whom a more intimate engagement is possible. She's definitely a more human person, a person who treads on the ground, just like all of us do. See you in the next episode of Literary Snippet.
Hi, my name is Gillette Sam, and I teach sociology at IIT Kanpur. Uh, One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So, if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So, that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So, let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. Can I just pick up my bags and hop on the next plane and go to South Africa? Any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So, we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other, correct? So, when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.